Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 19 on more ODEs.
In this lesson, we'll consider some new families of ordinary differential equations, their solutions, and what they're good for. Along the way, we'll learn some new methods and some new applications.
Among the many differential equations that you may encounter, a few families are worthy of note. Some ODEs are autonomous, meaning that the right-hand side depends on x alone and does not depend on t. Those equations that do depend on t are called non-autonomous equations. They can be very difficult to solve. Some, however, are solvable by the following separation method. If dx dt is of the form of a function of x alone times a function of t alone, then, following the pattern of what we did for the linear differential equation, we can separate out all of the x terms on the left, all of the t terms on the right. Then it makes sense to integrate both sides if these integrals are computable, and if you can solve for x, then you're in good shape. Let's look at an example. If you consider a body that is falling under the action of gravity, you'll notice different behavior depending on its shape. This is due to drag force. If we assume a drag force model where that force is proportional to the velocity of the body, then what do we have? Well, our body is being acted on by a gravitational force of magnitude m, the mass, times g, the gravitation constant, pointed down. Pointed upwards is the drag force that is assumed proportional to the velocity v by some constant of proportionality, kappa, the drag coefficient. Newton's law says that the mass times the acceleration, dv dt, is equal to mg minus kappa times v. And here we have an autonomous and separable ordinary differential equation. By doing a little bit of factoring and algebra, we can move to the left-hand side the quantity v minus mg over kappa, all in the denominator. On the right-hand side, what is left over is negative kappa divided by m dt. Integrating both sides, what do we do? Well, on the left, you have to think a moment to see that the antiderivative of dv over v minus a constant is in fact the log of quantity v minus that constant. On the right-hand side, the integral is very easy. It is negative kappa over m times t. We'll put our constant of integration on the right side. Now, to solve for v, what do? We exponentiate both sides. On the left, we have v minus mg over kappa. On the right, we have e to the negative kappa over m times t. That's times e to the constant of integration. We're just going to call that a new constant with the same name, c. Now, solving for v, what do we have? v is constant e to the negative kappa over mt plus mg over kappa. Let's think about this for a moment. If we take a limit as t goes to infinity, what happens? Well, the exponent in the exponential is negative. That means that term goes to 0, and goes to 0 rapidly. What remains is a constant velocity equal to m times g over kappa. This is called the terminal velocity. Depending on the value of kappa, it may be very fast or rather slow. Separable ODEs also arise in analysis of a fluid leaking from a tank. This is regulated by Torricelli's law, which relates h, the height of the liquid, with a, the cross-sectional area at the top. the law states that the rate of change of h with respect to t is proportional to the square root of h and inversely proportional to a. If we consider, say, a cone or anything where the cross-sectional area is quadratic in h by some constant, maybe pi, maybe not, then we obtain h prime is proportional to h to the negative 3/2. This is separable, and moving the h to the 3/2 over to the left side, and then integrating both sides, yields, on the left, h to the 5/2 times 2/5, and on the right, a constant times t plus an integration constant. Solving for h gives a linear function of t raised to the 2/5 power, where the constants will depend on the physics in your initial condition. What this implies is that h approaches 0 very rapidly at the end. How rapidly? It is in big O of the final time minus t raised to the 2/5 power. That comes into 0 very, very sharply when you're looking at something to a power of 2/5. Let's move on to a different class of non-autonomous ODEs. These are the linear non-autonomous ODEs. They're of the form dx dt equals a of t times x plus b of t, where a and b are functions of t. For example, dx dt equals tx plus 1/2 t squared is of this form. We say that it's a linear equation because if you suppress the t dependence, you get something of the form dx dt equals ax plus b. And that right-hand side should remind you of the equation of a line. Well, how do we solve such a problem? The method that we will introduce is that of the integrating factor. It's a little tricky, so hang on. Let us denote that integrating factor by I. We're going to multiply both sides of this equation by an as yet unknown function, I. Rearranging terms a little bit and multiplying through gives us I times dx dt minus ai times x, and on the right, I times b. Now, what is this good for? Well, if you look at that left-hand side and keep in mind the product rule, then you see something that should remind you a little bit of the product rule. If we had something that looked like I times dx dt plus di dt times x, well then, we would recognize that that's just the derivative of I times x. And that's something that's going to be helpful to us. So what would we need to be true in order to have this? We would need to have di dt equal to negative a times I. Now, focus on that, because what we're doing is deriving a differential equation for this unknown integrating factor, I. That is separable. That is solvable by the standard techniques that we've been using. When we solve that equation, what are we going to get? I is e to the integral of negative a dt, which we could write in shorthand as e to the negative integral a. If we choose such a function, I, and multiply both sides of our original equation by this, then what we obtain is on the left, the derivative of I times x. On the right, I times b. Now we can integrate both sides, because differentiation and integration undo each other. On the left, we have I times x. On the right, the integral of I times b. We can solve for x and obtain, after substituting in our formula for I, a scary looking but very useful equation. The solution is x is e to the integral of a times the integral of b times e to the negative integral of a.